Hello and welcome back to Discrete Mathematics. This week we're going to be talking about predicate logic. So predicate logic is just an extension of everything we've been doing with propositions and whatnot. We're just trying to add more complexity to the types of statements that we can make. So today we'll be talking about predicates and quantifiers. We'll talk about just translating qualified statements, literally just how do I get an English idea into a qualified statement. And then we'll talk about negation equivalences that we can use in proofs later on, whenever we have a predicate in our proof. So we'll start with the idea of predicate logic. We stated earlier on when we talked about statements that the statement, or not statement, x is even, cannot be a statement. And it can't be a statement because it doesn't have a true or false value. It could, but its true or false value is dependent on what you stick in for x, right? Like whatever the value of x is, that sort of decides whether or not this is true or false. And so x is even, not a statement. 5 is even, that's a statement, right? It's a false statement, but it's a statement. And so that's the idea. Sometimes we actually do want to express an idea in terms of something else, right? Some other value. And so a predicate is just a declarative sentence whose true-false value depends on one or more variables, right? Once you've given those variables a specific value, then that predicate becomes a statement, right? Again, x is even, not a statement. 5 is even, that's a statement. So we often use function notation to denote predicates. And so you can think of these as functions. There's actually a couple different ways of thinking about them. And sometimes in some sort of ideas that you're trying to express, it's easier to think of them in one way or the other. But here, we'll think of them as functions. So we can say that the p of x, we want to say that x is even, right? So p of x means that x is even. The other way you can think of that, though, is that p of x means that x has the property of p, which in this case is evenness, right? So p of x means that x has the property of even. You can have multiple variables, right? It can depend on more than one thing. So q of x and y, x is heavier than y. So here we can use that as a function, plug in x for x, y for y, and then see if that statement is true. So that means that, so these are predicates, right? P of x, x is even, is a predicate. Q of xy, x is heavier than y, is a predicate. P of 8 is a statement, right? 8 is even, that happens to be true. The Q of feather and brick, so feather is heavier than brick, is false. I suppose depending on the size of the brick and the size of the feather, but for the most part, we'll say false, right? There you go. You can make statements out of those predicates. Whenever you're talking about predicates, and I don't want to make this a big thing because it's really easy, a domain, and sometimes we call it a universe of discourse, which I think is what I learned when I went through college, and it definitely makes it seem a lot more, but it's just what can x possibly be? If you have something like p of x, is x an integer? Could x be a decimal number? Could x be your neighbor Bob? Could x be your cat? Right? I don't know, right? What's the universe of discourse? What can x be? In the case of even and odd, right, it's going to be integers. So x is going to be under the domain of integers. And we might actually state what that domain is while we are, doing our thing. I just need to know, is it integers? Is it the real numbers? Are these animals? Whatever. So the domain is all the possible values that you could use for your variables. So if you have an equation, right, standard math equation, x squared minus x minus 6 equals 0. We could turn that into a predicate. We could give it a value. We just say e of x. So e of x is going to represent that function. All right, sweet. So then we can say e of 3 is true, right? 3 squared minus 3 minus 6 does equal 0. But the e of 4 is false, right? Because it just doesn't equal 0. In this case, the equal sign is actually sort of playing the role of a verb. It is making the statement that I'm declaring that these two sides are equal. Whether or not they are depends on the value used for x. All right, so now we can do sort of English type ideas, and we can also do, like math problems. We can now start using quantifiers, because quantifiers are another way of turning those predicates into more of a statement, where you're actually defining not just a specific value, but more of a range of values, right? I want to say that, maybe, for every possible integer, this is true. Or maybe I just want to say that there is an integer for which this is true. And so we've got two different sort of quantifiers that we use on a regular basis. The first is a universal quantifier. This is an upside down A, but it stands for all. So for all x, p of x, which is in English, p of x is true for all x in the domain. So if the domain are human beings, for all x, p of x is saying that for every human being on the planet, they have the trait p, whatever that happens to be. 2 i's, something like that, right? Yeah. It's a universal quantifier. For all of the things in the domain, this is true. Now that is an actual statement, right? Because it's not just saying, oh, you could say that, oh, Bob has 2 eyes, or you could say, all humans have 2 eyes. Both of those have true, false values. So they are statements. I shouldn't say opposite, but the other, from the universal quantifier is the existential quantifier, which really found itself in college. I don't know. But the existential quantifier just means that there exists, right? So there exists an x such that p of x, right? There is at least one human that has 2 eyes, right? Whatever you're trying to say, there's at least one somewhere out there. So the way that those two quantifiers can work, the way that you can sort of bounce between the two of them if you need to, we'll talk about that sort of as we go and as we make sort of larger, more complex statements. So, so here's a quantified statement. Quantified statement would be, going back to e of x is just an equation. X squared minus x minus 6 equals 0. So I could say that there exists x such that e of x, right? What that means is there is some real number x, so this is over the domain of real numbers, so there's some real number x such that x squared minus x minus 6 equals 0. Or there's also usually an easier way to say it. There's the more like direct translation from what the actual symbols mean, and then the easier way is just say that that equation has a solution. Right? There is going to be a solution for this equation, which there is. So we got that. Now we can start doing some more stuff. If you were to, here we say there exists x such that e of x, right? That happens to be a true statement. This is not a true statement, right? So we can also say that, for all x, e of x. So it means for all the numbers, this is going to be true. All of the real numbers. Clearly that's false, right? So it matters whether you're saying, is there just a value, at least a value, or this is going to be true for everything. So, the real power of predicate logic comes from combining quantifiers and stuff together, so let's do that. We've already got a nice equation, the e of x. Let's do a new one. The n of x just means x is negative, right? So x is negative, well, n of x will represent that. Now we can say something like, there exists an x, n of x, and e of x, which is to say, there exists some number such that x is negative and x squared minus x minus 6 equals 0. Now, I think everybody took enough math to know that that's a parabola. Parabolas kind of go on both sides, and so this is going to be true. There is a negative answer to this solution. But, you'd have to prove it somehow. But point being, we know that that's a true statement, and we're now combining these things, these different statements together. So n of x, e of x are going to be ANDed together. Both must be true, and we say that there exists an x that you can use in those two statements so that that is true. Scope is kind of a simple concept. I don't know. Basically, when you say for all x, basically the scope is what x's are we talking about in this sentence? And so it's usually the parentheses right afterwards. If you were to get really, really complicated, expressions or really complicated statements, you might have something where it's like, okay, well, I've got for all of x, this and such x, and then it gets stuck into something larger that gets nested into something else, and then you've got an exists x over here. Well, then, okay, other than the fact I probably wouldn't use in one expression two different x's that just had slightly different scopes, you could. It's just the thing after the for all or exists all. How far does that apply? What x's are we talking about? Translation. So this is just how do I get from an English idea to an actual like predicate logic statement. And so there's not an easy answer. At the very end of this, I'm actually going to show a couple really common ones so that you can, for at least those, translate really quickly. But otherwise, you just kind of have to think about it and like what does it actually mean and go back and forth. English, obviously, is a very vague language, so not always the best. So if we use all cars as domains, we could say that P of X is X gets good mileage. So, P of an accurate TLs get good mileage, right? So P of X, X is good mileage. Q of X is X is large, so the car is large. So then we could say this expression here, for all X, Q of X implies not P of X, which in English would be for all cars X, if X is large, then then X does not get good gas mileage. That is the most literal translation of those symbols. For all cars X, if X is large, then X does not get good gas mileage. You could also say it in more normal English, right? All large cars get bad gas mileage. It's the exact same thing, right? In English, you would say it that way, but when you tried to translate it into sort of a predicate statement, right, a qualified statement, this is the way you'd write it. If you're saying all large cars get bad gas mileage, that means that for all X, if Q of X, then not P of X, right? If you have the quality of being large, and you do not have the quality of having good gas mileage. You could also say there aren't any large cars that get good gas mileage. Lots of different ways in English to say the same thing. So we can also do something like this, where we actually combine quantifiers into each other for different variables. So if we said for all real numbers, g of x of y is x is less than y, right? So g just stands for x is less than y. If that's the case, then we can say for all y, there exists an x, g x of y. So for all y, there exists an x where x is greater than y. Translated to English, for all numbers y, there exists some number x such that x is greater than y, or for any given number y, there is some number that is greater than y, which is absolutely true. For any number, you can always add 1 to it, you get a larger number. There is no largest number in math. And infinity doesn't count, it's a concept, not a number. You can always add 1. But now look at this one, right? So we've gone from for all y exists x. This is exists x for all y. Exact same things, but we reverse the order. And when you reverse the order of those quantifiers, it actually does make a difference to the logic of it, right? So again, exact same domain. G just means x is less than, or x is greater than y. So there exists x for all y such that x is greater than y. That would be that there is a number x that is so big that is bigger than all of the y's, all of the real numbers, which is false. There is no largest number, right? So exists x for all y, x is greater than y? No, it's the order of those things matter. And you can kind of get it in the English too a little bit. So going on to our third topic, last topic. negation. So eventually we're going to start using these predicates in proofs. So then how do you handle sort of a transformation, one of those steps when you have a quantifier? And the one that you're probably going to use the most is negation. And so we're going to have two rules for negation. We're only adding two rules to our list of proofs, but both have to do with negation. And hopefully the logic kind of makes sense here as to why you're making that translation. To sort of make it the simple thing, if you want to negate a quantified statement, all you have to do is pull the negation inward and then switch what the thing is. So if it was for all, it becomes exists. If it was for exists, it becomes all. So yeah, let's look at an actual example because I think it'll probably be a little bit better. In the domain of all people, let Lx stand for X is a liar. So if you have the property L, you are a liar. So this negation rule says if I want to negate the statement, all people are liars, that is the exact same thing as saying, if I want to negate the statement, all people are liars, right? So I'm not trying to prove all people are liars, I'm negating all people are liars. I could say there exists a person who does not lie, right? Who does not have the property of being a liar. So the opposite of all people are liars is there exists a person who doesn't lie. And the same would be true sort of the other way. If I wanted to negate the existential, right? So it's like there exists a person who lies, right? I could say, well, no, there is no person who lies. That's the exact same thing as saying, for all people, they don't lie. Anyway, the negation equivalence is you pull the negation in and then reverse what the actual for all or exists is. So then the last thing, this is just sort of like to help with some of the translations or some of the ideas, because if you get the wrong translation at the beginning, then everything you do afterwards is going to be flawed, right? And so getting it from English just into a formalized expression can be, yeah, it's part math, part art, right? So just because it's part English. So whenever you hear a sentence like all something are something, right? So all things are something. If P of X is X is the thing, and Q of X is something, then you could say for all X, P of X implies Q of X. In other words, if you have the property P, that implies you have the property Q. All things are something, right? All doctors are rich. P of X is X is a doctor. Q of X is rich. All doctors are rich. For all X, P of X implies Q of X. All fruit tastes sweet. P of X is a fruit. Q of X is X tastes sweet. So for all fruits, if you have the property of being a fruit, for all fruits, if you have the property of being a fruit, then you have the property of tasting sweet. I guess I should say for all foods, if you have the property of being a fruit. My universe needs to be larger there. But, and then the other one is, there is a thing that is something. So there's a whatever that is something. There is a rich doctor. There is a type of fruit that tastes sweet. That would just be exists X, P of X, and Q of X. So there exists X, something that has both properties. There is an instructor that is nice, right? That is a true statement, probably, right? There has to exist an instructor exists a person who has the property of both being an instructor and is also nice. All instructors are nice. Probably not true, right? For all, point being, you get the idea. Common constructors, there is a thing that is something. Your P of X is the thing, X is the thing, Q of X is the something, and then there exists X, P of X, and Q of X. You have both properties. That is it. So again, if you have any questions, send me a message through Canvas, and I'll see you online.